Hello, friends. Welcome back to You Can Do TV. Two thin strips of steel carry every train ever built. Under them sits crushed rock that quietly breaks down while 60 freight trains a day roll overhead. Millimeter tolerances, 4-hour repair windows, junctions that can shut down an entire corridor. Here is how the invisible limits of a railway actually work and what nobody sees behind it. Every railway ever built comes down to a very simple, very unfair problem. Two thin strips of steel have to carry everything. A freight train can weigh 15,000 tons fully loaded. All of it presses down through the wheel sets. A pair of wheels rigidly locked to one axle, moving as one unit. That is why a modern wheel set production line looks nothing like a workshop. Robotic arms place components with sub-millimeter accuracy. Self-driving carts shuttle finished assemblies to test rigs where sensors probe every surface for hidden flaws. You would think the hardest part is making the wheel round. It is actually making 10,000 of them identically round, month after month. Even a fraction of a millimeter off, and the wheel hammers the rail every rotation until something cracks. Now look closely at the piece nobody in the passenger seat ever thinks about, the axle. It is a solid steel bar linking two wheels, and it takes the full vertical load, plus every twist the train delivers on curves. Making one is not machining. It starts with cutting raw bar, heating it until it glows orange, then forging it under a press that shapes the shaft in a stage where temperature can drop within seconds. After forging comes heat treatment. Controlled heating and cooling to lock the grain structure into something tough. Then impact testing, tensile testing, microscope inspection. Fail one axle in service and you have a derailment. That is why every one of these gets tested like it might be the one that fails. The wheel itself is where physics gets harsh. A freight wheel can carry over 30,000 pounds of load, spinning at speed while grinding against a steel rail. Every rotation is a tiny impact event repeated millions of times over the wheel's life. Raw wheel blanks arrive as forged discs. CNC machines then cut the tread profile, the flange, and the hub bore to tolerances measured in fractions of a millimeter. The tread is not flat. It is slightly conical, which is what lets a train steer itself through curves without a steering wheel. Then comes ultrasonic testing, where each wheel is scanned underwater for internal cracks. Magnetic particle inspection under UV light catches surface flaws. One bad wheel in a fleet of thousands, and the whole safety case falls apart. Two wheel sets by themselves cannot carry a train. They need a frame that holds them square, absorbs shocks, and transfers load evenly. That frame is the bogie, and the Y-25 design under a freight wagon has become the workhorse of European rail. Springs go in first, then the frame lowers onto the wheel sets by crane. Every completed bogie hits a pressure test rig before it ever sees a track. All of that engineering just to make two wheels behave properly under load. Here is a question that sounds dumb until you think about it. Why can't you just bolt the wheels straight onto the locomotive body? Because the locomotive would rip itself apart on the first curve. Between the engine and the rail sits a chain of machinery designed to absorb every force the track throws upward. Overhaul facilities pull wheel sets and bogies off locomotives, freight wagons, and passenger stock. Then inspect every surface. Wheels get reprofiled on CNC lathes. The tread reshaped to restore the original geometry after service wear. Bearings come apart for inspection. Ultrasonic and magnetic particle testing hunt for cracks invisible to the eye. A worn wheel that looks fine can hide a fatigue crack waiting for its moment. Now for the piece that actually makes the wheels turn, the traction motor. In a modern diesel-electric locomotive, the diesel engine does not drive the wheels directly. It spins a generator, which feeds electricity to motors mounted right at the axles. Each traction motor has to deliver hundreds of horsepower into a wheel set while surviving vibration, temperature swings, and moisture that would kill most industrial equipment inside a year. Overhaul means stripping the motor down to bare housing. Copper windings on the rotor and stator get inspected coil by coil. Brushes wear down and get replaced. Insulation is tested at voltages far above operating levels, over 3,000 horsepower per motor group, and 40 years of expected service life. Are you kidding me? Between the traction motor and the axle sits a gear set, and this is where no margin for error stops being marketing language. The motor spins fast. The wheel spins slow. Gears bridge the gap by converting speed into torque. Precision gears for rail applications get cut on CNC machines that hold tolerances measured in microns. Spiral bevel geometry lets the teeth mesh smoothly under load. After cutting comes grinding, then coordinate measurement to verify every tooth profile. A gear that binds under load can shear off teeth mid-run, and 500,000 miles of warranty depends on that never happening. Upstream from the motors sits the actual power source, the diesel engine and its transmission. These are not car engines. A passenger rail engine can weigh several tons, run continuously for weeks, and gets rebuilt to standards tighter than the original factory specs. Then comes the piece nobody notices until it fails, the power pack and cooler group. Engines that big generate enormous heat. Cooler groups shed it. If you have wrenched on rail equipment for a living, tell us, what is the failure mode nobody warns rookies about? Threading through all of it are the hoses and hydraulic lines, the plumbing that keeps every auxiliary system alive. Pumps, motors, valves, all tested to 100% before leaving the shop. But even a perfect locomotive still has to hand its weight down to something below, and that something turns out to be surprisingly fragile. Here is the part of railway engineering that breaks most people's mental model. The rail is not what actually holds the train up. Under those two steel strips sits a layer of concrete sleepers. Under the sleepers sits a bed of crushed rock, the ballast. And under all of that sits the subgrade, the actual ground. That ballast is doing more work than it looks. It spreads the wheel load sideways so the ground below never sees the full concentrated force. It drains rainwater. It lets the track flex slightly under passing trains without cracking. But ballast breaks down. Rocks crush against each other under millions of load cycles until the sharp edges round off. Fine dust fills the gaps. Drainage fails. That is what a ballast cleaner is fixing. A moving factory on rails, it lifts the entire track, excavates the old ballast, screens the reusable rock, and drops it back, all while progressing forward. For small jobs, workers still tamp ballast by hand. Well, by handheld tool. Battery-powered vertical tampers pack the ballast tight under each sleeper. 2 minutes per sleeper. Quiet, clean, and low vibration for the operator's hands. But for kilometers of track, hand tools are hopeless. Enter the tamping machine that eats ballast for a living. These massive yellow machines straddle the track and drive tamping tines down into the ballast on either side of each sleeper. The tines vibrate at high frequency while squeezing inward, packing rock tightly under the sleeper. In one pass, the machine also lifts the entire track to correct geometry, restoring level and alignment lost to settlement. 60 passing freight trains per day, and geometry drifts millimeter by millimeter until something has to give. Fresh tamping actually leaves the ballast loose, which is a problem because loose ballast means the track will settle again the moment trains return. So right behind the tamper comes a stabilizer. Machines like this one combine tamping and stabilizing in one pass. Split-head tamping units can handle 2 sleepers simultaneously on plain track, then adjust to work around the complex geometry of switches. Roller clamps grip the rails and lift uniformly, even where sleeper spacing is irregular. The stabilizer then shakes the whole track laterally at controlled frequency, forcing the ballast grains to interlock and settle to their final packed state, before the trains do it by accident. The result, a track that behaves like it has already carried a month of traffic, released back to service the same night. Skip the stabilizer, and the first trains do the compacting themselves, which means the track keeps moving until it stops. Last comes the ballast regulator, the machine that sweeps and shapes the ballast profile back into spec. Excess rock gets pushed aside, missing spots get filled, brushes tidy the top, and then everything gets truly interesting the moment the track has to split in two. Straight track is honestly the easy part of a railway. The terror lives at the junctions. A turnout is the switch mechanism that lets one track branch into two, and it is arguably the most engineered 150 meters in any rail network. Pre-assembled turnout sections get built up at a nearby base site, sleepers, rails, and the moving switch blades, before being lifted onto the main line. Specialized gantry systems roll along an auxiliary track, hoist entire panels weighing dozens of tons, and slew them into precise position. One turnout, laid in one possession window. Get it wrong by centimeters, and trains cannot pass. Look at that. On a high-speed line under construction, the stakes climb higher. The trains that will run here move at 300 kilometers per hour. Cranes lift pre-assembled track panels off flatbed wagons and lower them onto freshly graded ballast. Workers with torque wrenches secure every fastener to spec. Alongside them, cranes swing long yellow lifting beams that carry sections of switchwork into place. Try tightening thousands of fasteners in the exact order a manual demands, at night, in the rain, and see how long your good mood holds. Everyone assumes high-speed reliability comes from the trains themselves. Junction engineers will tell you otherwise. Anyone want to explain where the real reliability actually gets built? But some turnout sections are too big for any conventional crane to handle. And that is where the track layer earns its keep. It runs on crawler tracks, so it works independently of the rails. Loading hooks slide under the base of the rail and grip pre-assembled turnout segments weighing up to 50 tons. Crawlers rotate 45 or 90 degrees, letting the machine sidestep across rough ground, past signals and masts. And here's what nobody warns you about. Even after the geometry is perfect, you still cannot simply run more trains. Two rails, two directions, unlimited trains. That is the intuition, and it is completely wrong. Every train occupies a section of track for a period of time. Add more trains and headways shrink until the system chokes at the busiest junction. Now add another factor. Track needs renewal, rails wear, sleepers crack, fastenings corrode, ballast fouls. And every meter renewed is a meter temporarily removed from the network. Enter the renewal train, a rolling factory hundreds of meters long that eats old track and lays new track continuously. Old fastening systems come off first, exposing the rusted rail-to-sleeper connections. A removal unit lifts each old sleeper out of the ballast and shuttles it back through the train. Behind it, a laying unit places fresh concrete sleepers into precise position. New rail rolls in on top. Flash butt welding joins rail sections into continuous ribbon, followed by grinding to smooth the weld. Old rails and scrap get recovered by magnetic crane. Fresh ballast pours in, gets profiled, tamped, dynamically stabilized, and brushed. Over 9,500 kilometers of track renewed worldwide by systems like this. But renewal is only half the equation. Sometimes you are laying track where none existed before, and speed becomes the whole game. On a new line, every day of construction means one more day of trains held up on older, slower routes. Enter the panel laying system. Instead of installing sleepers and rails piece by piece, the crew prefabricates full track panels, 18 meters of ready-to-lay track, off-site. Then a pair of self-propelled crawler trolleys carrying gantry cranes rolls onto the worksite. The trolleys are radio-controlled by one operator standing at safe distance. Working in synchronized pairs, the gantries lift each panel from a transport wagon, slew it into precise position, and lower it onto the prepared ballast bed. Then they retreat, and the next pair of panels arrives. The numbers speak for themselves. 11.6 kilometers of new track laid in roughly 15 days. Just 3 operators handle the entire radio-controlled system, with 645 panels moved and placed sequentially. Try laying that much track the old way, and you would still be somewhere in the first kilometer when the next election happened. On the French high-speed extension, they pushed the concept further. 500,000 tons of ballast, 250,000 sleepers, and long welded rails delivered directly from wagon to sleeper. Each rail bar runs 432 meters and gets thermite welded end-to-end into continuous track. In tunnels, ballast disappears entirely, replaced by concrete slab track that lasts decades with almost no maintenance. On the Bucharest metro extension, crews built 15 kilometers of embedded block system inside the running tunnels. Concrete blocks get positioned along the tunnel floor. Rails are placed on top and locked into precise alignment with special jigs. Fiber-reinforced concrete then pours around everything, encasing the blocks permanently. Add 23 turnouts, 5 double crossovers, and a third rail installed under high-precision jigs, and you have a metro track that will barely need attention for 30 years, which explains why the machines that keep all of this running never actually stop working. Here is the paradox nobody talks about. To keep a railway running, you have to shut parts of it down. And when the shutdown window is 4 hours between the last night train and the first morning train, every minute is currency. That is where the track renewal machine comes in. 82 meters long, 315 tons of steel rolling on the very rails it is about to tear out. The machine straddles the existing track and does something absurd. It removes the old sleepers, slides them out through internal conveyor belts, and drops fresh concrete sleepers into the ballast bed behind, all in one continuous motion. At the front, workers cut the old rail and splice new sections so a continuous length can feed through the machine's belly. Deep inside, mammoth tooth grippers hook under each old sleeper and yank it out. Portal cranes shuttle the old ones back and new ones forward on parallel conveyors. Planned output, 300 meters per hour. On a good night, they push closer to 400. You have 4 hours to replace track that took an entire day to build originally, and the first commuter train does not care about your excuses. 4 hours. But the trickiest maintenance work is not on plain track. It is on switches, and that is where this universal tamper earns its money. Regular tampers can handle straight sections easily. Switches are geometric nightmares, tapered rails, moving blades, tight tolerances, sleepers that vary in length as the two tracks diverge. A high-performance universal tamping machine handles all of it. Individually adjustable tamping units drop into the ballast at exactly the right position, packing rock under every sleeper regardless of angle. Roller clamps grip and lift the track evenly, even where sleepers sit at unusual spacings. 20 years from now, will maintenance crews still be sitting in these cabs, or will these machines run autonomously through the night? Where do you see it going? Pull back from any one machine, and you start to see the actual scale of this industry. Yellow machines working at sunrise, at dusk, deep in tunnels, on mountain bridges, in city yards. Different climates, different track gauges, different national standards. Same underlying task. Design engineers at CAD stations sketch new machines. Welders and grinders build the frames. Assembly crews mount hydraulic systems weighing tons each. Test crews commission every finished machine before it ships. And out on the network, operators work rotating shifts because ballast maintenance does not stop for holidays or weather. The result is a global fleet of specialized machinery, most of it painted yellow, that exists for one reason: to give trains back to the timetable as fast as possible. And even after all of this, the rail itself can still betray you. After ballast, geometry, and every possible piece of machinery, you finally come back to the thing that started it all: the rail itself. Steel takes a beating that no other structure in transportation infrastructure absorbs. Every wheel passing overhead delivers a compressive load, then releases it millions of times per year. Small defects grow. Weld joints become the weakest link because a rail joint is where two separate pieces of steel have to behave like one continuous piece. Thermite welding fixes that. A refractory crucible sits over the gap between rail ends. A chemical reaction ignites, pouring molten steel into the gap at temperatures over 2,500 degrees Celsius. Once cooled and ground flush, the joint disappears. 8 welds on one bridge project, each one inspected before a train ever crosses. But sometimes the only way to save a section of railway is to destroy it. When a rail is worn beyond repair, or a section needs replacement mid-run, out comes the hydraulic rail shear, a jaw mounted on an excavator arm that bites straight through the steel like it is cutting cardboard. The shear closes with tens of tons of force. The rail snaps in seconds. To keep the railway alive, sometimes the railway has to eat part of itself. Here is the twist most people never suspect. Behind the railway, you see, there is a second railway you never see. It has no passengers, no freight, no timetables. It exists purely to keep the first railway alive. And it starts with something wild. The machines that maintain the track need maintenance themselves. Tamping units get pressure washed, then cut apart with torches. Worn tines get removed. Fluorescent penetrant inspection catches hairline cracks. Build-up welding restores lost metal. CNC machining brings the geometry back to spec. The machine that fixes the track ends up on a test rig itself, sensors wired everywhere, screens watching every parameter. What a chain! Then there is the wheelset and bogie overhaul industry, an entire branch of engineering dedicated to giving old parts a second life. Up to 1,500 bogie overhauls per year run through one major facility, with a 48-hour turnaround option for operators who cannot wait. Wheel sets come off the vehicle. Brake equipment, suspension systems, and dampers all get inspected separately. Wheels go on to CN-controlled gauging and machining centers that measure every parameter before deciding whether to reprofile the tread or replace the wheel entirely. Axles get ultrasonic, magnetic particle, and eddy current testing to catch any hidden flaws. Bearings come apart, get inspected, and either return to service or head for scrap. Suspension tubes, axle boxes, final drive gearboxes. Every piece gets its own workflow. Skip one inspection step and a fatigue crack rolls back into service. That is why nobody skips. Beyond wheel sets sits an even wider workshop, one that overhauls the smaller components most passengers never think about. Air brake compressors and distributors, brake cylinders, disc brake actuators, slack adjusters, air reservoirs, hoses, suspension dampers and air suspension control valves, buffers of every type, electrical components and train data recorders. Over 4,000 train data recorders supplied worldwide. Every one of them a small black box that quietly proves who was right after something goes wrong. But some parts are too specific to buy off a shelf. And that is where rail fabrication shops earn their keep. A worn bracket on a 30-year-old locomotive? A custom housing for a modification? A one-off sheet metal panel for a legacy fleet? These jobs land in fabrication. Laser cutting machines slice sheet steel, aluminum, and stainless with precision measured in tenths of a millimeter. CNC punching handles patterns that would take hours by hand. Press brakes fold flat metal into three-dimensional shapes to exact angles. Welders work through the full range of techniques: MIG, TIG, spot, and stud welding, depending on what the part demands. CAD designers work directly with customers, sometimes reverse engineering a component from the last surviving example when the original drawings vanished decades ago. Somewhere in this workshop, a technician is rebuilding a part that has not been manufactured since the 1970s. Meanwhile, the wheel manufacturers themselves keep producing new stock, and their process is closer to art than industry. Steel gets heated to exactly the right temperature. Too cold and it will not form. Too hot and the grain grows coarse and brittle. An 8,000-ton press then shapes each wheel in one heat with no temperature loss between forging stages. Every wheel gets stamped, laser measured, hardened under water spray, and tempered for the right balance of toughness and hardness. Only a handful of European facilities are certified to produce high-speed rail wheels, and the tolerances tell you why. Turning, marking, balancing, ultrasonic testing, magnetic particle inspection, dimensional measurement, and painting. Every wheel goes through all of it, held to accuracy measured in micrometers. Robotic grippers move wheels between stations. Coolant sprays as CNC lathes finish the tread. Wheels get submerged in liquid for ultrasonic scanning. Any flaw, and the wheel never leaves the factory. And at the end of it all, wheel and axle come together on a hydraulic press. The moment where two separate parts become one wheel set for life. Automated pressing machines handle it now. Robotic arms feed bearings onto the axle. Conveyor systems shuttle wheels and axles to precise position. The press then drives the wheel onto the axle at exactly the force specified. Too little and the wheel slips. Too much and the axle deforms. Control panels record every pressing curve as proof. From this point, the wheel set gets a serial number and enters the world as one indivisible unit. And that is where the loop closes. From this axle press, the wheel set ships to a bogie assembly line and eventually rolls under a locomotive, carrying loads back onto the very network we started this video with. Every mile of railway you see is riding on limits nobody outside the industry knows about. Millimeter tolerances on components, 4-hour possession windows, ballast that quietly fails while trains keep running above it. As freight demand keeps climbing and passenger networks expand, do we double down on this maintenance-heavy conventional system? Or is the future actually slab track and automation on every corridor, ripping out ballast for good? Freight operators say ballast still makes sense on their tonnage. High-speed and metro planners keep choosing concrete. Neither camp is fully wrong, which is why the argument never quite ends. Tell us below where you stand. and whether you have watched either approach fail in a way that flipped your thinking. Thanks for making it this far. Punch that subscribe button to catch the next deep look at the machinery quietly holding modern infrastructure together. Plenty more heavy engineering waiting in the pipeline. See you. Take care.